be on this quarter.
Pay attention.
All right.
Oh, next week.
We are. We will not finish it by the end of the quarter. We are in chapter 3 now. So just a little different format with the notes, like I said. I'm just trying to condense and save some paper here. So chapter 3 is all about systems of equations and inequalities. This lesson is technically a review from Algebra 1, but probably like that second half of Algebra 1. So maybe you saw this before March shut down, maybe not. I'm curious to see. So 3.1, so I'll always put like the lesson title right here. We're going to solve systems of equations, and we're going to do it graphically and algebraically. Okay, so your warm-up for today is I want you to graph these two lines on the same coordinate plane. All right, so I'll give you about 1 minute to graph those. Good luck. Okay, I'm going to start graphing. This first one has a y-intercept of 8 and a slope of -4/1. Give a straight edge. All right, my second line here, I'm going to have to put into slope-intercept form. So that would be -2x divide by -3, we get +2/3 x for our slope and -6 for our y-intercept. Okay. So your line should look like this. Now, if I talk about like solutions to a line, that's every single point that lies on the line. All of these points would be solutions to this equation. You know how this to this one. Okay. And same with the red line. All of these points that lie on this red line. We're just graphing all of the solutions to this equation. So when we're talking about a system of equations, that just means we have two equations, two or more. Okay? For today, it's just going to be two. So if I want to find a solution that is a solution to this whole system, I have to look for the point that's a solution to both of these lines, aka a point that lies on both of these lines. You guys see a point that lies on both the blue line and the red line? Brayden?
3, -4.
3, -4, aka obviously where they intersect. That point's on both lines. Everybody's line should intersect here at 3, -4. 3, -4, that right there, folks, that point, that ordered pair is technically the solution to this system. System containing two equations. Trying to use my pen, it's not really working for me. So this system. Okay, so technically you just solved one by graphing. So our whole goal for today when we solve these systems is we're looking for the point where the two lines cross. Okay? This example says, of these 4 ordered pairs, what is the solution to this system? So you can see the system, I have two equations here. I'll call this top one my blue one, this one my red one. They want us to figure out which of these points is the point that lies on both lines, aka the point where those two lines were to intersect if we were to graph them. So I just start by checking if it's even on my first line. So let's just start with A here. The point 1, 1. Does the point 1, 1 lie on my blue line? Well, let's plug 1 in for X, 1 in for Y. Oops. And I get 2 equals 2. Is that true? Yeah. That means that the point 1, 1 is on the blue line. Okay, so we at least know it's on the blue line. Is it on the red line? Well, here I have 1 minus 3. And I get negative 2 equals negative 6. Is that true? No. So it doesn't even lie on my second line, so therefore it can't be the solution. We need an order pair that's on both lines, so it can't be this one. I'll try B next. B, 0, 2. Is that on my blue line? Yup. I get 2 equals 2. That's a solution to that equation. Is it on my red line? I get 0 minus 6 is negative 6. Oh, we found it. The point that's on both lines. So if we were to graph both these lines, that would be the point where they intersect. It would be B. Do I still need to check the other ones in case these are solutions?
Yeah.
Well, can two lines ever cross at more than one point?
Oh no.
No, so we don't need to check. But there is one special case where they do intersect at more than one. They intersect at literally every point, and that'd be if they are the same line. So technically you're not wrong, but I mean you could quick check them if you wanted to. You should only get one because obviously you guys learned that in geometry. Remember that postulate?
Yeah.
Oh, we just talked about this in geometry. Two lines intersect at exactly 1 point. Postulate, you learned that in chapter 2 when you did the fun proof.
I remember that.
Oh,
We skipped proofs.
Well, you skipped part of the proof. You still do chapter 2 a little bit.
Yeah.
You still did them a little bit.
Wait, was that like the proof, the big free problem test?
Yes, pretty much. No. You're gonna something else, I think. Okay,
Yeah.
we are going to learn 3 methods to solving systems. 3 methods. First, graphing, which is technically what you just did. Okay, so let's go ahead and do this one together. It's kind of fun if you use 2 different colors. You don't have to. I'll do my top one is my blue. So it says solve the system of equations by graphing. What that means is we're going to graph the 2 lines and find their point of intersection. So I solved this one for y. I'm putting it in slope-intercept form. So add x, divide by 6. Okay, I don't get the nicest equation. It just has fractions. But guys, we want to try and get exact points here because we're looking for a point where they intersect. So I would plug numbers in until you find a whole number point where these cross. Okay, so I kind of looked at this and I was like, hey, if I plug in like 3 for x, I get 1/6 times 3 plus 3 halves because I knew that 3 times a 6 is a half. I'm like, hey, I'm going to end up having a half plus 3 halves there. So we get 2. 3, 2. It's really helpful if you have a y-intercept that's a fraction to find a point, another point where to start, okay, when you're graphing. And that's just a general rule of thumb. Could we have lines where we never have whole numbers? Yeah. But for the most part, if you're asked to solve these by graphing, there's going to be some ordered pair that you can find. So 3, 2 is here. So like I said, it's just a little bit easier than just kind of guessing. That wouldn't be 3 halves, this would be 3 halves. Guessing where your y-intercept is because we're looking for exact points. We need to be as exact as we can. And then from there, I can graph my slope up 1/6. And do as many points as you can. That's really important for these. Okay, so you should be able to fit 4 points on that line. Does my y-intercept look like it's about 3/2? Yeah. Okay, but again, now we have exact points. So it's going to make our life easier when we go to actually try and find where these intersect. My second line here, this one isn't as bad when I put it in slope-intercept form. I subtract the 2x, divide everything by 3. Okay, always keep your slope as a fraction. We have negative 2/3 x minus 3/3 is 1. Nice. I have a y-intercept. That's a nice integer there, negative 1. And then I can graph my slope of negative 2/3. And hopefully you find one that's on both of your lines. And we did here. I like to circle it. And that ordered pair would be negative 3, 1. So if you were taking an assessment and I said, what's your answer? This is your answer. That's your solution to that system. Negative 3, 1. It's a point that lies on both of those lines. It's a point that's a solution to both equations. How could we check our answer if this is right? Plug them into both, just like we were just doing. Plug it into both equations and it should work in both. I would highly recommend doing that, especially when you're taking like a quiz and you're doing it algebraically. Okay, you can check by plugging them back in. You'll get 9 = 9. You'll get negative 3 = negative 3. All right, so that's one type of solution we could get with 2 lines. 2 lines could intersect at exactly 1 point, right? And we'd get one solution to that system. What are some other types of lines we could have? Yes?
The one you said where they're both together.
Yeah, we could have the same line. And it's hard to see here because you're like, I only see one line. Well, this second line, you can't see it. It's lying right on top of the other line when they end up being the same line. And they go on forever. The third case is we could have parallel lines, and we know parallel lines never intersect. All right, so here's how we classify these kind of like special solutions. If they intersect at exactly 1 point, we have one solution. So intersecting lines we get one solution. And it's the point where those 2 lines cross. Okay, that's what we just looked at a couple examples of. That is classified as consistent and independent. Consistent means you have a solution. Independent, think about what the word independent means. Alone or by yourself. Independent, one solution. Okay, so I like this one, and this is what Connor brought up of lines can intersect more than 1 point. How many times are these lines intersecting? A lot, right? They'd be here forever. Infinitely many. They're intersecting at every single point that's on their line. And he's going forever. So when we have the same line, we have infinitely many, and I like to do this, and I'm okay with you doing that. Infinitely many solutions. Do you guys do this in Algebra 1? Do you remember this?
I think, yeah, I remember something like this. Yeah, like, I remember Mrs. Volcom made us check every single one, and I complained about it. That's how I remember it.
I make my Algebra 1s check too. Okay, then the only other possible system we could have is if the lines end up being parallel, which meaning they never intersect. We call this an inconsistent system because there's no solution. There's no points that would lie on both lines. Therefore, there's no solution to the system. Okay, perhaps maybe the new vocab for you would be these words. Consistent means we have a solution. So we either have one solution, so that's consistent and independent, or we have infinitely many, that's consistent and dependent. How I remember that is if you have 2 lines lying on top of each other, that top one's kind of depending on the bottom one to hold itself up, right? If I were to move this line, that line would fall. So when they're right on top of each other, they're dependent of each other. That's how I remember it. And then if there's no solution, we just call that an inconsistent system. Okay, so let's practice classifying these really quick. This first one, you can see we have two different equations here, but they end up being the same line. How would I classify that?
Consistent, independent.
Perfect. Consistent, because there are solutions, there's infinitely many. And dependent. So if you're to graph and you get two lines that are the same line, you'd have infinitely many solutions. This one. Whoa. What's my classification here? Cindy?
Consistent, independent.
Thank you, ma'am. Consistent and independent, she says. You can see independent, we have exactly one solution. And when I have no solution, we say inconsistent system. Okay, there's your new vocab for the day. Probably don't use that algebra one.
I think we did.
Oh, you did? Okay. Okay, moving on to our two algebraic methods. These are usually crowd favorites because not everybody loves graphing. So they like doing either substitution or usually eliminations, kind of the people please, the favorite of the crowds, I usually think. Okay, so we still have a system. We still have two equations, and we're still trying to find the point where these lines intersect. We're going to do it without graphing, and these methods are actually better because if our lines were to cross at like 2/3, negative 1.1 repeating, we would never be able to see that from a graph, right? It'd be really, really hard to approximate that exact answer, but using algebra, we could get those exact answers. All right, here's a step-by-step of substitution. So if you're stuck on your homework and you forget where to start, just look back at this. It kind of like walks you through it. But we're going to do two together. These are two separate examples here. So you can draw a little line through these. Okay. So the first thing I kind of tell my students, I'm going to color coordinate these again, is because substitution starts with an S, I tell them to start off by just kind of like separating the equations like this, like writing them side by side. And usually this will kind of help students remember what to do next. So I say, oh, substitution, start with separating. Okay, so you can see step one in our list there. It says solve one of the equations for one of the variables. The variables that are the easiest to solve for are the variables that have a coefficient of 1 or negative 1's pretty easy as well. So I look here at my blue and my red equation. Does everyone see how my blue x has a coefficient of 1? That one's going to be my easiest to solve for because all I have to do is add over the 7y, add over 7y. I'm not graphing, so I don't have to solve for y. And there we have it. Boom, solve for x. Pick the easiest to do. Will it still work if you decide to solve for this y, this red y? Yes, but you're going to have a lot of fractions. Okay? Now, sometimes you might have to if there aren't any with 1's or negative 1's. All right, step one is done. Solve one equation for one of the variables. Here's the substituting piece. And think of like when you go through the drive-thru and you're like, instead of fries, can I get onion rings? And they like substitute your order. They take out the fries and they put in the onion rings for your side. That's what we're going to do here. We're going to take out the x of my other equation. We're going to substitute in 11 plus 7y because according to my first equation, that's the same thing. Okay, so we have 5, take out the x, replace it with parentheses, plus 4y equals negative 23. Substitute in what x is equal to, which is 11 plus 7y. That's a 7. That looks like a 2. We can do that because that's what x is the same as. And then you should be left with an equation that has only one variable that you can solve. All right, so here I would distribute the 5. Okay. Combine my like terms, I end up getting 39y plus 55 equals negative 23. Subtract 55. You get negative 78. Divide by 39. we get y to be negative 2. All right, that's step 2. Step 2 says substitute into the other equation to replace variable, then solve the equation. Done. All right, now remember, our answer is an ordered pair. Our answer is a point where these two lines cross. Obviously, I just found the y-coordinate. The y-coordinate is negative 2. I'm not done. I gotta find the x-coordinate, right? Every ordered pair needs its match. So, since you have this nifty equation over here, this is why I like to write it side by side, you just go back over here, you're like, hey, I know x is the same as 11 plus 7 times y, and now I know that y is negative 2. X is the same as 11 minus 14, x is negative 3. So my answer, folks, so when I'm going to box here, my answer is negative 3, negative 2. If you want to check it, because you have no visual here, you have no graph, plug it back into both, and it would work. All right, does that ring some familiar bells? No. Oh, good thing I assigned some homework for you guys to practice on. Care about your learning. Okay, we're going to do one more substitution. So let's go ahead, let's separate them. So I like separating them because it's like, you do this, you go back here, you go back there. It's just a lot of substituting. All right. What a fun lesson for Monday. All right, between my blue and my red x's and y's, which variable and which color is the easiest to solve for in this system? Kaola? Okay, the red equation, which variable? X or Y? X, because there's a negative 1 in front. So all we have to do is add over the 3y. One little extra step here, divide by negative 1. Make sure you divide everything by negative 1, so we get x is negative 3y plus 6. Does it matter if you have the negative 3y or the 6 first? No, it doesn't matter. You can add it in any order. So if you added over the 3y and did negative 6 plus 3y and then divided by negative 1, doesn't matter. All right, first step is done. Bless you.
Thank you.
Now we do the substituting one. Now you're not always going to take out x. You're going to take out whatever variable you solved for. Okay, in both of these examples, we just happen to solve for x. But if we were to solve for y, we would have to take out the y out of the other equation and substitute that one in. Okay, so make sure you're substituting the right variable. X is the same as negative 3 plus 6. So we're going to take out the x from the blue equation. Replace it with parentheses.
I have a question.
Yes, sir.
Could you technically divide everything in that equation by 3 to reduce it, make the math easy?
Yeah, you could.
Okay.
Totally. Great question. Substitute in what x is the same as. And in that step, guys, you should just have x's or just have y's. Okay, if you have x's and y's, then you did something wrong there with your substituting. Because you should be left with something that you can solve. All right, let's go ahead and do some algebra here. And here I go to combine my like terms, and I have 9y minus 9y, which is 0. Not y, it's 0y. If I said y, that's the same as 1y, and you're telling me that 9 minus 9 is 1. And I end up getting, these kind of like drop out here. Those are 0. I end up getting 18 equals 18. So what this means is we're going to have one of these special types of solutions. This either means we have infinitely many solutions or no solution. If the statement is true, what do you guys think that means? Infinite or no? Infinite or all real numbers. Yep, you can say all real numbers too if you'd like, if that's what you're used to. All real numbers and infinite mean the same thing. This means we have infinitely many solutions. Your book uses infinitely many. I'm familiar with infinitely many. If I was left with something like 0 equals 18, that's not true. That's no solution. Okay. There's substitution. Method 2. So method 1 is graphing. Method 2, substitution. Method 3 is elimination. Substitution and elimination, those are like in our algebraic category. So if it ever says solve by an algebraic method of your choice, that means you get to pick substitution or elimination. But technically graphing isn't algebraic. So, all right, here we go. Elimination. So just like it sounds, we basically try to eliminate one of our variables, either x or y. So what we try and do is we try and get the coefficients of one variable to total 0. So what I mean by that, if I were to look at the x's, right now those total 5 of my two systems. Right now my y's total 4. I want to try and manipulate my equations here so that my coefficients total 0, or that I have the same number in front but different signs, like 3 and -3 or something like that. So what we can do is we can multiply the equations by a number as long as we multiply everything in both sides so that we can get matching coefficients with different signs, aka get them to total 0. Okay, so I'm just kind of looking at my x's here because those numbers are smaller, and I'm like, hey, I'm thinking of a multiple that 3 and 2 both go into. I'm like, I could make those both like 6 and -6. So what I'm going to do in this one, in my blue equation, I'm going to multiply that one by 2. So write it like this in parentheses. Sometimes it helps people to do it on both sides like this also, because you have to multiply that whole side by 2 and this side by 2. All right, so my new blue equation here ends up being 6x minus 10y equals 16. This actually kind of goes back to like what Connor said, like if we were given something like this, could I divide everything by 2 and get back to there? Yeah, it's the same equation. All right, now my red equation, I'm like, all right, I'm trying to eliminate my x's. I want this to be a -6. I want it to be a -6 because that would total 0 when I add these together. So what could I multiply my red equation by? -3, yep. And again, if it helps you write this one over here, you can. So just remember to multiply everything by that number you choose. And that's different every time. And that's different for anybody who's doing this problem. Maybe Connor was trying to eliminate the y's and chose to multiply and make them -45 and +45. Doesn't matter. So here I end up getting -6x minus 27y equals +21. Okay, so that's basically that step 1. Multiply one. Sometimes it only takes multiplying one of the equations by something, or both. In this case, we had to do both by a number to result in two equations that contain opposite terms. So now you can see my x's are opposite terms. Step 2, what you're going to do is you're going to add these equations together like old school math where you add the digits all lined up. So keep your x's lined up, keep your y's lined up, keep your equal sign lined up. We're going to add these together, and 6 plus -6 is 0, and that's our goal. This is why this is called elimination. Those are gone. -10y plus another -27y is -37y. Carry down your equal sign. 16 plus 21 is 37. Then solve the equation. I just have a little one-step equation here. All I got to do is divide both sides by -37. And I get y is -1. And now I have half my answer. Y is -1. So it looks like I'm going to get one solution here. All right, now with elimination, there's no handy-dandy little equation that we like had solved for x. So you just go back and plug it into one of the originals to solve for the other variable. So I just use this one. 2x plus 9y equals -7. So it says substitute and solve for their variables. So now we know y is -1. So I have 2x, that'd be -9 equals -7. And then we just solve this. Add 9, we get 2. Divide by 2, we get x is 1. So my solution would be 1, -1. Box that. Because I have people on tests say, I don't know what my answer is. I'm like, well, think about it. When you're graphing, what do you look for? Point where they cross. Great. Answer should be a point. You want to check it, plug it back in. Should work. Do you guys remember elimination?
Is factoring in this unit later?
Later, yeah.
Mm.
Well, I don't know if it's in this chapter. I have to look at the outline. I don't think it comes up in systems, actually. It will be eventually. Okay, let's try one more with elimination. So here, just for sake of this, let's say I want to eliminate the y's this time. Look at my y's. I have a -8 and I have a 32. So I really only need to multiply the top equation by 4, and that would give me a -32y. So I'm like, wow, this is set up beautifully. I don't even need to change or multiply my second equation by anything. All right, so let's go ahead. Let's multiply this by 4. So remember, you have to distribute it to everything. We get the equation. We get 12x. I'm just going to write it right underneath my red one, so I don't have to rewrite it. Minus 32y equals 96. And now, again, my goal is to eliminate y. I can see, sweet, they are set up that they're opposite terms. I have 32 and -32, so that would be 0. Those are eliminated. All right, add together my equations. I look over here and I have -12x plus 12. I wasn't trying to eliminate these, but it happened. What do I technically get as a total on this side?
0.
0, nothing. Careful here. 96 plus 96, those don't eliminate. Right? 96, if it was -96, they would. 96 and 96 is 192. Is that a true statement?
Not yes.
No solution. Okay, and obviously no solution and infinitely many, that can come up at any time. It can come up when you're graphing. If you got 0 equals 0, that means infinitely many when you're doing elimination. Okay, so just be on the watch for some of those special ones. And there you have it, folks. That's lesson 3.1. Thanks for watching.